I will introduce Tom Bachmann, who will be telling us about the eta periodic motivic image of J.
Okay. Well, thanks very much for the invitation. Let me try to get on my way. Well, of course, yes. So the first thing is that this all joint work with Mike Hopkins. Okay, so now let me begin with the math. And so first of all, I'm going to fix a field. Call it K. And also throughout, I'm going to have some assumptions, specifically 2. I don't want it to have characteristic 2. And this is important, and I really don't know any way around it. And I'm going to assume this. So I'm going to assume that the so-called virtual two-etile cohomological dimension is finite, which if it doesn't mean anything to you is pretty irrelevant. So every finitely generated field, for example, or finitely generated over an algebraically closed field, or I mean, every sort of reasonable field tends to have this property. And also at the end of the day, everything I'm going to say, well, no, sort of the main result is true anyway for all fields. So it's just a technical thing, which you don't have to worry about. Okay. So let me begin with a small number of recollections. So the first, well, okay, so I'm going to talk about motivic stable homotopy theory. So I hope you have some idea what this gadget is, right? So this is the motivic stable homotopy category. And I mean, maybe I want it to be the motivic stable infinity category or whatever, but let's not mince words. And so in there's of course the unit spectrum. And so this unit spectrum has an important graded endomorphism, and it's called eta. So that's where the eta comes from in my title. So in this category, you somehow have bi-graded suspensions corresponding, well, to the two spheres, which we tend to have in the motivic world. And so there's this very important map called eta, because it's somehow related to the topological eta. But in contrast to the topological situation, this is not nilpotent, right? So no composite of the iterated composite of this map, you never get a zero map, which I suppose was proved by Fabien Morel. And okay, so I'm going to discuss this. And then there's also some guy which is called little kw. So this is a particular eta periodic spectrum. Okay, so it's a motivic spectrum over the field K which we're working. And it happens to, it has the property that if you sort of smash it with the eta map, you get an equivalence. It doesn't really matter to right now what it is. So it's a so-called connective cover of capital KW, which is the so-called Balmer spectrum representing Balmer-Witt groups. But again, it's not super relevant right now, and I'm going to hopefully tell you everything you need to know about it. So, I mean, let me do that right now. So this is a ring spectrum. And I can tell you it's homotopy groups. And notice that usually, of course, in motivic homotopy theory, we have bi-graded homotopy groups. But if you have an eta periodic spectrum, this sort of eats up one of the gradings in a trivial way. So I'm mainly going to just use these singly graded homotopy groups. And they are obtained as follows. So they're given as follows. You take the Witt ring of your field, and then you adjoin a polynomial generator. And this is called beta. Barth element, it has degree 4. And the Witt ring, well, this is the so-called Witt ring of symmetric bilinear forms, or quadratic because we know the characteristic 2. So this is a certain invariant of your field. If it's R, the field is R, for example, then this happens to be Z. If it is the complex numbers, then it happens to be Z mod 2. And I mean, in general, it is whatever it is. It can be a bit complicated. And which is, by the way, also the same thing as the zeros homotopy group of the eta periodic sphere. Again, I suppose this computation is due to Fabien Morel, and it proves in particular that eta is not nilpotent because this ring is not zero. Right. So now let's get to the meat of it.
So Tom, can I ask about beta? You're writing that beta has degree 4, but like in the bi-grading, I should probably think of that as like 8 comma 4, right? And then,
yes, so I'm going to very consistently move everything into sort of weight 0, but yes.
okay, great.
That's right. So Jean Fazel and Olivier Otion. So I mean, this KW guy, this is sort of the name indicates, is some sort of K-theory thing. And I mean, one of the important things which you can do in K-theory is these so-called Adams operations. And so Jean Fazel and Olivier Auchon, they've constructed these Adams operations. Again, I'm not going to give you a full story, but certainly they have proved that there exists a map, which I will call psi3. And it goes from sort of KW, but now I need to invert 3 on it to itself. I guess only in the target is where I really need to invert it, but whatever. And this map has a number of properties, which I'm going to use. So one is that this is a ring map. And the other is that they tell us what it does on beta. So if I right, so in homotopy, I can apply this map to the element beta, and it turns out you get 9 times beta. And there's another fact which I'm going to use all the time, but which is more trivial, which is that sort of on pi 0, which is the Witt ring, it acts trivially. And I mean, this is just because the Witt ring, of course, already lives in the sphere. And I mean, everything is sort of linear over the homotopy of the sphere. So this is not very difficult. Okay, so now let's try to fight our way towards this motivic image of J spectrum. And it's actually quite easy to build. So the following lemma, which I'm not going to attribute to anyone, because again, it's pretty simple. So, all right, so I look at my connective Witt K-theory guy. And so if I want to do this Adams operation psi3, I have to invert 3, and I can do a bit more. I'm going to invert all the primes other than 2. So let me localize it at 2. And then I will map to itself, and I could do psi3. But what I'm going to do is I'm going to subtract off an identity map, right? So this stable, motivic stable homotopy category is in particular additive. So I can form sums and differences of maps. So I take this difference. And what I can also do is I look at the fourfold suspension of KW. And then I map to KW by just multiplication by beta. And so the first observation is that I can fill in an arrow here. And I mean, in fact, there exists something here. Let me call it phi, because it exists uniquely up to homotopy, right? So I mean, there's only one map basically which you can put there so that it commutes. And this is going to be very important for us. And all right, so here's one more thing which I can do. I can take a fiber of this new map. And I will, yeah, so the main business is to compare this to the unit somehow. Right, so this guy here was a ring, so there's a unit map in. And again, the claim is that this compares with the fiber of phi in an essentially unique way. So there exists an essentially unique map here. Again, it's unique up to homotopy. And so this lemma is fairly straightforward to prove using the T structure on motivic spectra. And I mean, basically, I told you everything that you need to write. I mean, basically, the only thing which you need to know is this knowledge about the homotopy groups of KW, and then this is all pretty straightforward. So let me try to connect to my title, which is that this fiber of phi is what's called the motivic eta periodic image of J spectrum. So for reasons which I'm not at all going to get into and which are completely irrelevant for this talk, it's often referred to as that. Okay, I'm not going to use this word again, but I can now state the main theorem. Which is that, well, I said that we're trying to compare this fiber of phi with a unit. And of course, the fiber of phi is too local and it's eta periodic. So I can also make the unit two local and eta periodic to make the comparison better. And it turns out that then actually it's an equivalence. So the canonical map, so I start eta periodized two local units, and I map it into the fiber of phi. And I look at this in the motivic stable homotopy category over my field K with the assumptions that I had. And this is an equivalence. And so basically what I want to spend the rest of the talk on is to give you some indications how one might go about proving this. So this has a number of really nice consequences. For example, it allows you to compute all the eta periodic homotopy groups of the sphere, motivic sphere, and also you can compute things like eta periodic, algebraic, symplectic cobordism, and whatever. But so, well, I'm going to focus on how to try to prove this, and I hope it's going to be interesting. Right, and so what I will try to indicate is why this induces an isomorphism on homotopy groups. Right, so one more thing to say is that this result actually is true in much greater generality. So, I mean, we stated it for a field K of characteristic not 2 and finite VCT. And I mean, the finite VCT assumption is completely irrelevant to begin with. Not for the proof, but so the result is true for any field of characteristic not 2. In fact, it's true basically for any scheme on which 2 is invertible with some correct interpretation of, like, I guess this term. But well, again, we will try to be more down to earth and look at this sort of computationally accessible case of a nice field. Okay, so how are we going to do this? Well, this is somehow a two-local problem, and in an obvious way, it sort of splits into a rational problem and a two-complete problem. And sort of rationally, this is easy. So the reason is that we know if you take the eta periodic sphere and you rationalize it, then we know all the homotopy groups by something called motivic Serre finiteness theorem, and it's just the Wittring tensored with Q. I mean, in degree 0, you get what you have to get, and everything else was just torsion, so it's sort of irrelevant. And so on the other hand, you can just easily compute what all the homotopy groups of the fiber of phi are. I mean, particularly, you just take this rationally, you have this rational Wittring, and then you just multiply by some like 9 to the n minus 1, which is a non-zero number. And I mean, you can compute everything, and it's clearly an isomorphism. That's not the problem. Right, so then really what we do is we concentrate at 2. So we may as well complete at 2. May complete at 2. And so now how we're going to go about that? Well, so it's a problem somehow in homotopy, and I would like to, so there are various possible ways which you can approach this, and I'm going to explain one of them. And so it's a problem in homotopy, and what I want to do is I want to reduce it to a problem in homology, because, well, optimistically speaking, often homology somehow is easier, right? So what's homology going to mean? Well, I introduced a new spectrum for you, call it HW, and it's just the cofiber of beta on KW. Right, in other words, its homotopy groups are the Wittring in degree 0 and nothing else in other degrees. So that looks like a reasonable thing for homology, right? And it's also sort of in the T structure. If you take the zeros sort of object for the sphere, you get the same thing. So that seems like a reasonable notion of homology. And then, because this is somehow everything is connective, instead of proving that this map is an equivalence, we can instead sort of prove it after smashing with HW and then also with 2 completed. So it suffices to prove that, so this map, I take this unit and I smash it with HW, of course, you just get HW, then I complete it, goes to, so this fiber of phi smashed with HW to complete it. So it's enough to prove that this map is now an equivalence. And well, okay, so that's what the meat of our the main part of our work is going to be. So it's going to proceed in two, I suppose, pretty natural steps. So the first step is that we compute the sort of the HW homology of little kw two-adically. So I compute this. Okay. And then in the second step, well, you have to work out what this phi guy does in homology, and then sort of check that you get the right thing, right? So we know all the homotopy groups here because it's just a two completed Witt ring. So we need to figure out what the homotopy groups here are, and we have to check that in degree 0 you get this Witt ring, and in all other degrees you get 0. Somehow you have to prove that. So now we know that it's the fiber of the Adams operation on this guy. So we now have to figure out what, well, assuming we know what this is, we need to figure out what the Adams operation does and then compute the kernel and co-kernel and whatever. And hopefully there should be lots of cancellation. Right, so the step 2 is to compute the action of phi. And then somehow we're going to be done. Okay, so without too much further ado, let's start this fight. So obviously I'm going to start with step 1. Right, so what we're supposed to do is we're supposed to take KW, smash it with HW, and work out somehow the two adequately completed homotopy groups. But I mean, how can you compute anything sort of from nothing? Well, sometimes you can come up with some ingenious argument, but so in general, we need to use some sort of standard technique. And so the usual techniques which you can use is something like the Adams spectral sequence or the Adams-Novikov spectral sequence. And the problem with this is that it always will give you some eta completed thing. And if you start with something eta periodic, then for sure you're going to get 0. So that's not going to be the correct answer. But so the way this has been addressed, I mean, yeah, so I should say that other people have thought about this kind of problem over various fields. And the way in which they've addressed this is always what they do is they do some related eta complete calculation, and then they invert eta, and then they argue that this somehow is the answer that we want. And in order for this sort of thing to have a chance to work, you somehow, as a starting point, you need to know that some things are eta complete for non-obvious reasons. And so the starting point which I offer is the following theorem due to myself and Eldon Elmanto and Polane Ostwar. And this is now where I'm going to use my assumptions on K. So let E be a so-called very effective spectrum. So this is a certain reasonably well understood subcategory of spectra. And then if you two-adically complete it, by some magic, it's already eta complete. So I think something like this was claimed maybe for the sphere spectrum in an influential article by Hugrich Ormsby. But to be honest, I did not really understand the proof. And so this theorem here is proved by adapting some technique of Mark Levine using the slice tower. But in any case, this is going to be our starting point. Well, eventually this is going to be our starting point. Right, so now I know I want to do this computation here. And unfortunately, so the only ways I know of doing this are all a bit complicated. So I'm going to have to introduce a whole bunch of new spectra. So more players. Going to enter the ring. Oh, that's too many S's. Okay, so what do we have? Well, one spectrum, which is going to be very important, is little ko. So this is some sort of motivic analog of connective orthogonal K theory. And if sort of thing means something to you, it's the very effective cover of the so-called Hermitian K theory spectrum. Right, so let's say very effective Hermitian K theory. On the other hand, there's there's some other version of homology, which is called motivic homology. And now I need some slightly more esoteric spectra. So one which I want is K upper W. And you can get it, for example, by taking the sphere and you mod out by a certain element called H. And then you take a sort of its zeros object in the homotopy structure. And this is the so-called unramified with K theory spectrum. Whew, what else do we need? Right, I need unramified Milnor K theory. And this is just pi 0 of HC mod 2. Okay, and well, I'm not expecting you to know all of these spectra and all the important properties, but let me give you some facts so that we have a chance of proving something. So what are the facts? Well, I'm going to want to use this theorem here. So I better tell you something about very effective spectra, and it turns out that sort of these guys all are. So KW, maybe some suspension, and also KO, they are very effective. Okay, then, so we're trying to do some related computation where if I invert eta at the end, I get what I want. So I better tell you what happens if I invert eta on these guys. So if you take KW and you invert eta, or capital, so this capital K upper W, and if you invert eta, it turns out you just get HW, or homology. And on the other hand, if you take a little KO and you invert eta, you get little kW. So this is beginning to look promising, right? So I want to smash these two together. Know the homotopy groups, of course, I'm going to smash these two together and somehow work out the homotopy groups there. Right, and then I'm going to use that there exist the following cofiber sequences. Basically, I'm going to work out what happened. Yeah, so let's say I take my unramified with K theory and I mod out by eta in the sort of spectrum sense. And the cofiber is unramified Milnor K theory. And this is basically equivalent to what's called Milnor's conjecture in quadratic forms. And I'm going to use one more cofiber sequence, which is -1 HC mod 2 goes to HC mod 2 multiplication by some element called tau. And the cofiber is again Milnor K theory. And this is more or less the Bloch-Kato conjecture. So these are some seriously big guns, but all right, let's see where they get us. And then there's one more fact. Well, not really even a fact, but the point is, you might ask, for example, what's HC mod 2 smash HC mod 2? Or what's HC mod 2 smash KO? And I'm not going to give you the answer, but the point is these are all known, and it basically looks like in topology, right? So these are going to be some sums of HC mod 2s, and with some shifts in them, of course, and twists. And I mean, it's very infinite, it's sort of Steenrod algebra type thing, but it can all be worked out. Okay, so now how does this help? Well, so what I'm going to do is I'm going to take little KO and I smash it with this capital KW. And so basically I want to know what its homotopy groups are, maybe after eta completion. And to do this, well, first I'm going to mod it out by eta. Now what happens, of course, if I take the unramified with K theory mod out by eta, then I get Milnor K theory, which was the same thing as taking HC mod 2 modding out by tau. So that's the same thing as KO smash HC mod 2 modded out by tau. But you see, I told you that this is known, right? So it means that this whole thing must also be known. Of course, I mean, it would maybe be easier to work out what's happening if I would tell you exactly what it is, but then also there would be loads of huge indices. So let's not go too far into details. And then what you might hope might be possible is that you try to compute the homotopy groups of this guy up to eta completion from the homotopy of groups of this guy by some device, and that device is of course called the Bachstein spectral sequence. And you will get the bigraded homotopy groups of KO smash KW eta completed. I mean, of course, there's no guarantee that this is going to work because there's some spectral sequence and it's like an infinite amount of work in general to figure out what it converges to. But in this case, you look at exactly what you get, and then sort of it collapses at E1 or E2 or whatever the page is, and you find some explicit answer. And then you invert eta, and you find the following explicit answer. So I don't want to take you through the pain of working out how it happens, but you take KO smash KW and you complete it at eta, and then you invert eta. And the answer turns out to be, well, you get either 0 or you get the two-adically completed Wittring. So you get the Wittring two-adically completed if star is bigger than 0 and congruent to 0 mod 4, and otherwise you just get 0. Okay, so in other words, we're getting this extremely regular answer. It's like the Wittring 0, 0, 0, Wittring 0, 0, 0, which, by the way, is exactly the same thing as the homotopy groups of this guy. Well, sort of after eta periodization, right? So the homotopy and the homology are somehow the same, at least on the level of abelian groups. Of course, the Hurewicz map is not an isomorphism, but okay. And so now we're just going to connect this back to this theorem here, right? So what I'm claiming is that this computation is basically what we wanted, right? So I took KO smashed with KW and I eta completed it and I eta inverted it and I two-adically completed it. Now, eta inversion preserves sort of two-adic equivalences, so I can just as well complete it on the inside also. So that's the same thing as taking KO smash KW, completing it at eta and at 2, inverting eta and completing at 2 again. And then we use this nice theorem, which tells me that if I only completed 2, I'm already eta complete, right? So I can throw this out because of this Bachmann thing. Okay, but then since I'm eta completing on the outside again, 2 completing on the outside again, I can just also ignore this, right? It's completely irrelevant. But now I can just invert eta in these guys. So this is going to be the same thing as, well, little kw smash hw, two-adically completed. So then the upshot is that this thing which we computed here is indeed the homotopy groups of this guy, which we were after. So this means that step 1 is finished. So and what we have to do is we somehow have to figure out how this Adams operation, or this modified whatever Adams operation type thing, how it operates on these groups, right? So remember that basically this Adams operation is sort of, it does some degree 4 thing. So it's going to connect all of these groups in some way. And we need to figure out how. Okay. So we do our step 2. So basically you look at, well, so I mean, there's just sort of the trivial part, which is somehow in pi 0, right? So you look at pi 0 of this fiber of phi. And I mean, this is just the two localized Wittring, simply because, I mean, there's nothing sort of in degree -4 which can interfere with this. So this is fine. And pi 0 of sort of HW, two localized, is also the Wittring, two localized. And the map is easy to see is an isomorphism. So really, I mean, we don't really care about pi 0. So what we need to prove is that pi I of this fiber, so I should smash with HW. Smashed with HW, two-adically completed, let's say, is 0 for all I bigger than 0. And so if you look at what this means in terms of this fiber sequence which we were doing, in other words, we need to prove that this phi map, which goes from, let's say, pi 4n of this thing here, kw smash hw, two-adically completed, goes to pi 4n minus 4 of the same thing, then this should be an isomorphism. And I mean, in fact, we know what the groups are, right? We just computed what it is. So this group here is, well, it's isomorphic to the two-adically completed Wittring. This is also isomorphic to the two-adically completed Wittring. And somehow we have to check that this map, which comes out of this Adams operation by lots of not very direct functoriality, or I mean, I guess this computation coming out of some spectral sequence thing is also not very direct. And somehow we have to work out that this map is an isomorphism for every n greater than 0. Oops, for all n greater than 0. Okay, so that's what we're going to do in the last 10 minutes. And so what I'm going to do is I'm going to pull one more rabbit out of the hat. So one more player. And this is going to be something called the algebraic special linear cobordism spectrum. All right, so what are we going to use about this? Well, one thing which we're going to use about this is that we know its homology. So Alexei Ananievsky thankfully has computed this for us. So what he says is that if I take, let's say, KW, smash it with MSL, and I want to know what the homotopy groups are, well, what you get is basically, well, the homotopy groups, of course, of the KW, so this is the Wittring of K adjoint beta. And then there's going to be a polynomial ring over that. So there are going to be some generators, let's say P1, P2, right? Basically sort of Pontryagin classes. If you remember how in topology, you can somehow compute the homology or cohomology. I guess now I'm doing homology, so sort of not really Pontryagin classes, but some dual thing, but one can work it out. And it's a polynomial ring like this. And so the Pi is in degree 4i. Yes. So that's one thing which I'm going to use. And the other thing which I'm going to use is that we can work out something about the Adams action on this homology, right? So this guy here, of course, again, it has an action by this phi operation, or even just by the Adams operation psi. And it's also not necessarily obvious what it is, but one can work it out. And so what you find is that if you do psi 3, I suppose I have to invert 3, of course, in order to do this. And I do it to pi, then what you get is basically you get pi, and you get beta times pi minus 1. Right, so notice that the degrees of pi and pi minus 1 differ by 4. So if I multiply by beta, I'm in the same degree again. So this is pretty reasonable. And then there's some other error terms. So I'm just going to write plus order beta squared or I. So I, this thing here, I have not used so far. This is the so-called fundamental idea. So this is some particular ideal in the Wittring. In fact, the quotient is Z-mod 2. All right, so now what does this buy us? Well, first of all, I can compute what the phi does, not the psi 3, right? So I compute phi of pi. And remember what was this phi thing? Well, basically we took psi 3 minus the identity, and then we somehow lifted something along multiplication by beta. So what this tells me is that if I take phi and I multiply by beta, I get psi 3 of whatever minus whatever. But this ring here, this ring here does not have any beta torsion, right? So there's a unique way of dividing by beta. It may not be possible, but there's only one way. So what I learned is that this is just going to be psi 3 of pi minus pi divided by beta. And I know that a priori the division must be possible. And well, now I put in what I computed, right? So this, so it's this thing here. I subtract off pi, so this goes away. I divide by beta, so this goes away. So it's going to be pi minus 1 plus order of either beta or I. So there's some arrow term, but basically the phi somehow connects the pi one after another. And right, so now we're really getting to the end. So the corollary of this is that this map phi, which was from pi 4n of kw smash hw to identically completed to pi 4n minus 4 of the same guy. Now I'm modding out by I, so I get just the field with 2 elements. And the claim is that this map is not 0. So why is that? Well, maybe I want to use this. So let me write, it's not 0 over here. So that's to save some space. The proof is not so difficult. I have some map from MSL to HW, sort of canonical map. So I can look at the induced effect on homology. This map is fine. Like this. This map is also phi, and this commutes. And well, so I'm just going to ask, what does it do to, so I screwed it up. Okay, well, how do I fix it? I guess I do it again. Sorry about that. Tried to be too clever. So I want to prove that this map phi is non-zero, and what I'm going to prove instead is that if you do phi n times, it's non-zero. So I'm going to do this, pi 4n of kw smash hw to identically completed goes via n times phi pi 0 of kw smash hw to identically completed modulo I, which is also f2. And now I do the same thing with MSL again. So it's pi 4n of kw smash MSL to identically completed phi n pi 0 of kw smash. No. Like this. Okay, so now I'm gonna run my argument. So I have pi here, right? Now if I apply phi once, then I get pi minus 1 plus some arrow term, which is multiples of beta and multiples of phi. So I apply phi again, so I get pi minus 2 plus some arrow term, which is still multiples of beta and multiples of I. So I do this n times. What I get is p0, which is like implicitly 1. Okay, maps to 1 plus possibly some multiples of beta and some multiples of I. By the way, there cannot be multiples of beta because just for degree reasons. So let me just plus order I. And then this map here was a ring map, right? So if I go to here, I get 1. But then this tells me that this map here is not 0, right? Because if I go this way around, I also have to get 1. And so surely this map cannot be the 0 map. And well, that's the end of the proof. And that's also basically the end of the proof of the whole thing, right? So now we just get to the punchline, which is we were working with this two-identically completed Witt ring, but because of the assumption that the virtual cohomological dimension is finite, this is the same thing as the I-identically completed Witt ring. And this is in fact a local ring. Right, and so what we're trying to prove is that, So what we're trying to prove is that this map here, which is basically just you take a free module of rank 1 of your local ring, maps to a free module of rank 1 over that local ring, linearly over that local ring, is an isomorphism. And then you see by Nakayama, this happens if and only if basically it's an isomorphism on residue fields, which for F2 just means it's non-zero. Right, so therefore, this phi map, which whatever, right, so the phi map which we wanted is an isomorphism. And so this is the end of step 2. So I have like 3 minutes, and I could say something like you can compute the homotopy groups of MSL, but maybe I will just say this is the end.